want to take just a brief moment to talk about how computers use matrix exponentials. We've seen how it's a more general method, which means it's more complicated, but what are some things about it that work well for computers? Let's start with the definition. Okay, well, in the series form, we're simply adding powers of the matrix. And computers actually work really well with multiplying matrices and adding terms together. Now so the real problem is having an infinite number of those things happening. Well, if you notice, as we power up the matrix, we're multiplying it by a smaller and smaller quantity. T could be growing, that's true. I mean, you could have time that's, forward in time, maybe 10 seconds, 15 seconds, etc. And 15, to a k power is pretty big, but it's not as big as k factorial, whatever that k is. K factorial grows faster than any polynomial, any t. No matter how big t is, k factorial will catch up with it as k goes infinity. So at some point, we can say, that's enough. These terms are small enough, they're negligible, and we drop off a certain number of terms. So computationally, we only need to compute a certain number to attain a relative accuracy. And we will choose how far out you want to go to define that accuracy. The other interesting thing is that when you're solving systems that have time incrementing, you can actually take the matrix exponential once and then use that or use a form of the matrix exponential to increment in time. And you don't have to do this, truncated sum again and again. So let's look at it. If we discretize in time, instead of thinking of all possible values for time, we choose all discrete values of time that are a certain width apart, a certain time step apart. Delta t apart. So we choose a time step, and that allows us to have the initial time, usually 0, and then we add delta t to get the next t1 time, then t2 time, etc., etc. Now let's just assume that t0 is actually 0. Then we write down our matrix. We have e to the atn as e to the na delta t, and the only thing that's changing here is this n, and it's changing by an integer, so we can take e to the a delta t and power it up. So we find the matrix exponential for a small time step Or you can think of this as the delta matrix exponential. And then we can use that delta, e to the a delta t, power raised to the nth power to get e to the a t1, equals e to the a delta t, e to the a t2 equals e to the a delta t squared, and so on. And so you can actually create a delta matrix exponential, which is based upon a small matrix expanded outwards so that you can truncate your series rather abruptly. And then from this delta matrix exponential, then we just power it up using integer multiples to find out how it changes with time. Well, why is that important? Well, our solutions are all based upon it. So we write x of t. Well, that's really time at some index in the future. So for a homogeneous solution, for example, we get e to the a delta t raised to the nth power times our initial condition vector, x naught. And to find out, that's an n by the way, to find out what xh at t1 is, we simply take e to the a delta t times x naught, and then find out what xh at t2 is, we just take e to the a delta t squared times x naught, which is really just e to the a delta t times xh of t1. So we can even reduce down the matrix powering times a vector repeatedly into taking the previous solution, e to the a delta t times x naught, and then powering that up by multiplying it by the next delta matrix exponential, and then to get to x h at t3, the next solution point, we then take our delta matrix times the solution at the previous point. So this is a clever way of reducing all the possible matrix products into simply doing it once and then again and then again and then again and then again, all the way through. And notice this is not the Euler's approximation method. This is actually the exact solution, with some approximation formed in how far out you truncate the matrix exponential. So if you could keep all the components, the solution would be exact, but of course we have finite space, so we can't. So the approximation is not in creating the method at the beginning and estimating there. We actually approximate at the end. We choose how much of the polynomial DNA, the Taylor series, we keep for that matrix exponential, and then based upon how much we keep, how much data we're able to have on it, we will have a certain precision in our solution all the way through. All the way through. Okay, so that is an eye into some of the computational usages of these matrices and the matrix exponential itself.